So the linear equations you're looking at are really kind of part of something that we practiced just the other day. Let me remind you of some of those things here, where you had a statistic versus a parameter. What is the difference between a statistic and a parameter? How come I'm using like X bar here? What does that mean as opposed to, say, maybe mu? How do I distinguish one versus the other?
Mu is the population mean.
Good. This is the population mean, and this is
The sample.
the sample mean. Yeah. So one of them deals with a sample, one of them deals with a population. As far as standard deviation goes, what would these symbols be for standard deviation?
Sigma.
S and sigma. Good. We had another one that we introduced just the other day with correlation. What was that? R and rho. Good. R-H-O. Rho. And we're going to do one more today. This is going to be a linear equation. So the statistic is going to be y hat, and I'm going to write a little different than I have over here, is b1x plus b sub 0. So that's a predicted equation. And then here's your observed equation, y equals beta 1x plus beta sub 0. Yeah, sorry to continue assaulting you with Greek letters, but that's just the nature of a math class. So we have to understand what these are. But what I want to start with, and there's a Desmos link on D2L right on the announcements page, is a reminder of what this is all about. Those are equations of lines. They have the form of y equals mx plus b. Can anyone remember? I know this is not an algebra class, but you were supposed to take it. Yeah, that's your slope. And what was b?
Intercept.
Your y-intercept. Nice, nice. So your slope and your y-intercept. Let's take a look at that link and kind of play around with the slope and the intercept. So if you open up that link, you might have to click and turn this on. I also always go to the tool icon and click capital A there, or the darker of the two. Makes it a little bit easier to see. But you can just play around. You can change the slope, whatever you want, between -4 and 4. Now, regardless of the slope, this is going to be your y-intercept. So right now, it's at 1.4, but I can change that. I can raise it up and raise it down. Right now, I've got a positively sloped line. That means as you move from left to right, it increases. If you have a negatively sloped line, then it does the opposite. Move from left to right, it decreases. But there's something in between that's worth paying attention to. And that's this line right there. That's a line with a slope of 0. It's horizontal. Now, with any other slope, knowing the value of x tells you the value of y. So for instance, let me make that maybe a nice even 1. Come on, a little more. There we go. If x equals 2, y equals 6. That's pretty easy. If x equals 4, y equals 8. Again, nice. If I give you the input, you know exactly what the output is. But when when the slope is 0, it really doesn't matter what the value of x is. The value of y is always just the same. So in this case, it's y equals 4, regardless of the value of x. So you don't need to know what x is in order to appreciate and understand what the value of y is in this case. For other cases, yes, but not in the case of the slope of 0. That's going to be a special case, and we're going to return to that later. For now, let's look back at our handout for a second. And one of the questions on the homework that you're going to see is to choose the correct answer below. So the correct answer below is in reference to these equations. What's the difference between those two equations? See what you can come up with. Give that a moment's thought. Which one looks good? A or B?
B.
I gotta vote for B. Some seconds? All right, yeah. The first equation is for sample data. That's this one right here. That's perfect. Notice your y hat. Y hat, that's going to be your predicted value. As opposed to this one over here, just a plain old y is your observed. Observed value. So it's the difference between y and y hat as to your observed or predicted value. So the first equation is for sample data, all right, that's this one right here. The second equation is for your population, which is typically what we've done with our sample and our parameters, our statistics and our parameters. Parameters are always in Greek letters. So, okay, that's the first one. Let's open up another link here. And I really do want you to open up this link. So from D2L, it's going to be the third link down here. What does a least squares regression line mean? This is a nice interactive link, and I want you to follow along because it's what I wish I would have had when I was a statistics student and learning about, well, what does a least square regression line actually mean? So this one, no, not that one. There we go. It should open up for you something that looks like this. Is that right? Okay. Now, a least square regression line eventually is going to try and fit a line to your equations, to your data, in the best way possible. The best in some sense that we're going to define in just a minute. So what's the best line that represents this data? Well, there's a lot of lines you could use to represent that data. Start by clicking that first circle here on the left-hand side, and that's going to put a red line on your data. Now, the cool thing about that red line, you can play with it. You can move it around. You can do anything you want with it. So whatever you think, try and figure out what line looks like the best line for this data. You can move these anywhere you want. Some lines will be good, some lines will be bad. You know, it's just going to kind of depend. So move it around and then see what you think. You know, what line looks the best to you? Now, all our lines are going to be different. That's okay. But how good is this line? How much of an error are we making? So in this case, these green dots, that's our data. Those are the observed values. Our predicted value is on the red line. So the distance between the green dot and the red line, that's an error, or sometimes called a residual. So let's look at and appreciate what those residuals are. Click the second circle underneath here. And now you see those lines here. And you can move this around to try and shrink some. Maybe some of the other ones get bigger, but some of them are going to get smaller. And what we want to do is we want to make this as small as possible. But there's some problems mathematically just trying to minimize these values. So for convenience, instead of minimizing these values, we're going to minimize something kind of related to this. What if I took this number, and that is just a number, it's just the distance between, say, 21.575 and the actual observed value, whatever that is, 26 something. That distance is my residual. Instead of dealing with that distance, which is, somewhere between 5 and 6, we're going to square that number. So let's look at all the squares of these numbers by clicking the next circle, or 2 circles down from what you've done. It should give you something like this. Now, you can still move around your line, but take a look at the effect on these squares. Sometimes they can get really big, sometimes they can get really small. If you've paid attention to the title of the handout or some of the things you'll see in the section, then it's a least squares regression line that you're trying to figure out. And the least squares refers to these squares right here, the square of my residuals. You're trying to minimize the square of these numbers, the sum of all of them. So not just one of them, but all of them. This one, this one, this one, so a bunch of these. So what line is going to do that the best? So, well, I mean, it's kind of a little subjective right here, right? But try and find the best line that you can. See what you can come up with in terms of, you know, a good looking line. See what you think is pretty good. In this morning's class, I did pretty good. I'm not quite as successful in this class, it doesn't look like. Maybe some of you guys are better than me. But moving around until you think you've got a good line. Got a good line, Elijah? No? No? But you think Dallas has a better line? Or do you got a better line? He's got a better line? All right. Dallas, you seem pretty confident. Scroll down a little bit and you'll see a little line here. It says sum of squares. What number do you have in your sum of squares?
It was 56.
Whoa, that is a real good line. 56. So, what are some other values that you got? Somebody else? Matthew?
61.
61?
I got 57,
57?
57.
57? 58? You guys are killing me. Mine's 76. Wow. In my morning class, I got down to 57.21, but right now I'm just not doing that well. I don't know what's wrong. But the least squares regression is going to minimize this total. That's where you get the least squares from, is you're minimizing the squared error here. So all these squares for all your data, the line that makes that total the smallest, that's going to be your least squares regression line. Now, if you want to see that actual regression line, you can click down here. That's the actual line, so you can see I missed it considerably. Okay.
On the nose.
Yeah, were you on the nose? All right, if you got around 57, 56, then you were spot on. You were right on the nose. So, boy, even with this, I'm not doing so good. 69, I don't know. Let's get away from this. There's an operator error there someplace. All right, but that's the sense in which you have a least squares regression line. So it's kind of cool that you can see that, because that's not an appreciation I had until much later in my statistics career. Think back to what we just did. And think back in particular to your residual. So which one of these best represents what you think of as maybe being the residual, which is the difference between your observed and expected? Omar, what do you think? Which one of these looks good? What do you think the residual is? A, B, C, or D? Which one? D? Residual is a value that is determined exactly without any error. It'd be nice if our lines determine things without error, but residual is just kind of the difference between the observed and the expected. So let's remind ourselves that Y is the observed. What's Y hat? And one,
Expected value.
your expected value. So your residual, sometimes going to be denoted with an E, is the residual. And that's just going to be the difference between the observed and the expected. Y minus Y hat. It's your error. I think that's why they use an E for this notation here. But that's actually going to be C down here. Residual value is the value of Y minus Y hat, which is the difference between the observed and predicted values. So that one is our residual. All right. Are we okay with that?
Yes.
All right, thank you. Let's move on down to example B. Different hotels in a certain area are randomly selected and their ratings were obtained online. Let me just switch over to this right here. No, wrong one. There. Using technology with X representing the price, X representing the ratings and Y representing the price, we find the regression equation has a slope of 130 and a y-intercept of negative 365. Complete part A below. So it says, what is the regression equation? Well, as a reminder, the regression equation is going to be made up of the slope and the intercept. So right here. But we got to choose which one of these four seem like it's going to fit. There's two of these we can eliminate right away. Can anyone see which one of these choices we can eliminate right away? Which two? Because we're trying to find the regression equation. And that's going to help us predict values of Y based on values of X. Which one of these looks like it's related to the prediction?
B and C.
B and C.
B and C, good job. B and C have a Y hat, and that's related to your prediction. So it means we can get rid of A and D. Must have Y hat, not Y. And that's for both of these. Must have Y hat. So that leaves us with two choices then, B or C. So what do you like of what's left, B or C?
B.
B, good. Why? Why B? Have I talked about an X hat?
No.
No, I didn't. There's no such thing as an X hat. So, yeah, I know, a little bit tricky. Now, the last part of this is you have to put this in the right order. So the way they're writing their equation is, basically Y hat equals B plus MX. That's not the order that I like to write things in. It's just a habit of mine that I do it with Y equals MX plus B. But, addition is commutative. You can put it in either order. Look through the problem and figure out the numbers that you need to put in here to get this problem right. How would you finish filling it in? And I've kind of highlighted him here for you. So what would that look like then? Haley?
For their format, it would be y equals negative 365 plus 130x.
Perfect. So the way they wrote it, it would be this, negative 365 plus 130x. So on my stat lab, when you do this at home, you're going to have to plug in those numbers into here. And then you get it right. Sweet. All right. Let's talk about the hypothesis test that we're going to do in this section. And thanks, Haley. So let's see. Hypothesis test. So in section 10.2, we're going to be testing b1x plus b sub 0. We're going to be testing whether or not the slope of our regression line is equal to 0. Now, why are we worried about that? What does it tell us if the slope of the regression line is 0 versus it's not 0? Well, let's go back to our Desmos presentation that we started things out with, which was right here. Let me remind you, there was something special about a line with a slope of 0. A line with a slope of 0 means I don't need to know the value of x in order to know the value of y. That is, it's pointless to know the value of x, because the value of y is the same regardless of the value of x. That's not true for any other number. So if I have a slope of 1/2, then knowing the value of x tells me the value of y. That's great. But for that one particular value, knowing the value of x doesn't tell you anything about the value of y. All right, the value of y is just the same regardless. So we want to know when this is true. If this is true, then you have a significant regression. So if you fail to reject, or if you reject h0, then you have a significant regression. So let's see. If you reject h0, then you have a significant regression. And what does that mean? It means that the slope of the line is different than 0. That knowing the value of x gives you information about the value of y. By the way, as kind of a brief aside, the hypothesis that we're testing in this section is tested with the same test statistic as what we had for the last section. And for the last section, it was correlation equals 0 versus correlation was different than 0. It's the exact same test. StatDiz doesn't do any extra work in testing one of these versus the other one. It's the same test. In fact, if you think back to the menu that we went to when we did this in section 10.1, it was labeled correlation and regression because it's the same test. Okay. Now, as far as your predicted values are concerned, whether or not you reject h0 is going to make a difference as to what you're going to do for your predicted value. Predicted value. So there's going to be two different possibilities here. Case one, if you reject h0, if you reject h0, then you're going to use the model. Y hat equals b1x plus b sub 0. If you fail to reject h0, Then your best predicted value is this. What do I mean by that? Y hat equals Y bar. What do you think Y bar is going to be? What would, if this was X bar, what would that be? Yeah. It's just going to be the average value of Y. That's it. That's the best you can do for your predicted value. So depending on your data, you know, and if you reject H naught or not, your prediction is going to be based on either this model or this model, one of those two. And so what we're going to do next is we're going to practice both of those just to kind of get in the groove, and then I'll give you one to look at. And it starts with example C on your handout. I'll do it up here. So for 15 randomly selected speed dates, attractiveness ratings by males of their female date partners, X, are recorded along with the attractiveness ratings by females of their male date partners, Y. The ratings are from 1 to 10. The 50 paired ratings yield all this information. What we're going to test is whether or not we get a significant regression and correlation. So we're really going to test this hypothesis. H0 such that beta 1 equals 0, H0 such that beta 1 is not equal to 0. And they're going to ask us to make a prediction based on this. I want to know what my best predicted value is in the case that I think it was X equals 7. Yeah, so X equals 7 is where we want to make our predicted value. So right here. But before we get there, we got to decide, well, which one are we going to do? Are we going to be using this model after we reject H naught, or this model after we fail to reject H naught? And to answer that question, we got to look through at some of the numbers here. The first number that we're going to need is the p-value. Second number we're going to need is the significance value. Between those two values, we can decide what we want to do with H naught. Are we going to reject H naught or fail to reject H naught?
Fail to reject.
All right, so we've got 0.052. And that's greater than 0.01. So Matilda's telling us fail to reject. Do we agree with that?
Yes.
Yeah. If the p value is low, H naught must go. Well, this is not low. It's bigger than our significance level. So fail to reject. That means our Y hat is really going to be the average value of Y. That's it. There's no real prediction here beyond just, you know, well, what's the Y value equal to? And I think they gave us a Y bar was 6. So that's your predicted value. Y bar is 6. That's it. Done. So it kind of feels like a lot of work for just that little result, but you know, that's the best you can do it sometimes. Are we okay with that first one?
Yes.
All right, got a couple thumbs up. Tahara, Lily, thank you. All right, so let's take a look at the next page then. So that's this one down here. For 50 randomly selected speed dates, blah, blah, blah. So a lot of the stuff is the same, but there are a couple changes here. In the second one, the p-value is 0.045, and we got a significance level of 0.10. So let's highlight those for just a moment. We're still going to be testing the same null and alternative hypothesis. That is h sub 0 such that beta 1 equals 0, and the alternative is that they're not equal to 0. Are we going to reach the same conclusion this time? Yes? No? What do we think? This time, p is less than alpha. If the p-value is low, h naught must go. So you're going to reject h naught. Great. Reject h naught. So that means we have to do a little bit more thinking then. Our regression equation is actually given to us right here in the output. Y hat is, and I'm going to write it a little bit differently. I'm going to write it as negative 0.361x plus 8.32. We want to know what y hat is when x equals 6. So what's our best predicted value when x equals 6? Okay, let's figure that out. So I'll plug in a 6 for x, and I'm afraid we're going to need to take out our calculators, unless you're really good at math, or maybe I should say arithmetic, and calculate something. See what you get. And keep your calculators out in case you need it for the next part too. So that 6 is coming from here. So if a male rates his partner as 6, what's the female going to rate him back as? Yeah, I'm getting 6.154 as well. So just doing the arithmetic here. So, okay, this is your predicted value. So a little bit different than the last one. Because we rejected it, we actually used the equation for y hat as opposed to just the mean. And there's one more like this in this series. So let's take a look at it up here, or you can look at it on your sheet. Suppose the IQ scores were obtained for 20 randomly selected sets of couples. The 20 pairs yield X bar is all this, etc. So there's a lot of data in there. Find the best predicted value y hat, given that the wife has an IQ of 94. So the X values, that's the wife's IQ. The Y values, that's the male's IQ. So, okay. While you look at that, I'm just gonna make sure I get something else open. Okay. So let's think first of all about our null and alternative hypothesis. H naught such that beta 1 equals 0. HA, beta 1 is not equal to 0. What's our decision here going to be? James, what do you decide based on the information in the problem? For H naught. Reject H naught or fail to reject H naught?
Reject.
Reject. Yeah, the p-value is smaller than alpha, so reject H naught. Reject H naught. So that means we're going to use this regression equation to make our predictions. So I'm going to rewrite it as 1.02x minus 2.77. You're free to keep it the way they read it. But we now want to make a prediction when we have an x of 94. So let's put in that x of 94. So here's our 94 coming from up here. What'd you guys get? 93.11. Okay, so that's your predicted value. So depending on whether or not you reject or fail to reject, you're either going to use the regression equation or you're just going to use the average value of the y's. It's going to depend on your decision for this part right here. So that's what I want to kind of highlight here, because when you're doing this at home, you're going to need to make sure you use the right method. Otherwise, it's just going to mark you wrong and probably not give you too much feedback. Okay. Let's actually get our hands dirty with some data. Are we okay with that last example? Example C. When to use which equation, when to use the regression equation, when to use just the mean. All right, a couple nods on that, thank you. This data set is in a link that you can get to off of Desire to Learn. So, oh man, really? Excuse me a second. But it's a data set for section 10.2. So you open up that, that's a Google Doc. And that should take you here. This example F. No, I'm gonna get a little further over. So you can go down to the page for example D and copy some data, and we're gonna paste that data into StatDisk. I should already have that data into column 1 and column 2 over here. So there's my data. So this is draw a scatter plot and a regression line. What's the value of R squared? Well, we're going to talk a little bit about the value of R squared in just a moment. But for right now, we're going to test H naught such that beta 1 equals 0 versus beta 1 is not equal to 0. And try and decide, does our regression line have a slope that's significantly different than 0? Hopefully yes. We'll find out in just a minute. It also asks us about a scatter plot and the value of R squared. So we have to figure out what this R squared is all about. We'll do that in just a minute. So going back to StatDisk. Hopefully you've copied things and put the data in. So when you're ready, go down to analysis. And like I mentioned earlier, there's a nice link between regression and correlation. They're the same hypothesis test. So that's when you go to analysis and you see that that's the same link. Column of x's is the first column, column of y's is the second column, and you click evaluate, and you get these results. At least I hope you get those results. You guys matching me? You getting the same thing? 0.0041. So with that, Lily, what do you think I should do with my null hypothesis here?
You should reject H naught.
Yeah.
Because the P is lower than the significance.
Yeah, our p-value is lower than any reasonable alpha that we would think of. So looking good there. Now it asks us about a value of r squared. So we're gonna have to go back and remind ourselves of a couple things. And the first one is, well, what's r, let alone r squared? Now r is stuff that we covered last time. Does anyone even remember the name of r? It was only like 3 feet long. R is the linear correlation coefficient. Okay, linear correlation coefficient. Wow, quite a mouthful there. What does R tell you about a line between pairs of y and x? Yeah, how linear it is. So R measures the strength of a linear correlation. Measures the strength of a linear relationship. If you remember, what did R range between? What was the minimum and maximum that R could be? Good, -1 to 1. All right, -1 and 1, those were your perfect negative and perfect positive linear correlations. So that's when all the data landed on a straight line. Kind of going back here to section 10.1. Here's kind of a quick reminder of that. There's your perfect negative relationship. Right here, all the data fall on a straight line with a negative slope. You could also have all the data fall on a straight line with a perfect positive slope. Now, values closer to 0 really mean that the data is just a jumble, that there's no real relationship between x and y. You're getting a value of 0 down here, not because there's not a relationship, it's just that there's not a linear relationship. So that's what R measures, is the strength of a linear relationship. How do you think I would get from R to R squared? Yeah, just square it. And it's literally that simple. If I gave you the value of R and asked you for the value of R squared, you'd square it. That's literally all you're doing here. R squared is the coefficient of determination. Now, not that I don't want you writing anything, and it's a good spot to write it, but this is also on your handout with a little warning, admonition to know this for the rest of your life, especially for exams. Hint, hint, all right? But let's talk about R. Let me write it down here so we have them together. R squared is called the coefficient of determination. Oh, boy. There we go. Determination. Coefficient of determination. This measures the proportion of the variability in Y that is explained by knowing the value of x. In other words, how good of a job does x do in predicting what y is? That's what it's asking, or that's what it's telling you. So let's go back and think about the value of r squared then for our current plot. Now, one of the outputs from our regression data is going to be the value of r squared. Take a look at your data. Take a look at that plot. What is it telling you? What do you see for the value for r squared? Let's see, r squared. Yeah, 0.76745. Yeah, you're looking at the adjusted r squared, which, I mean, there's good reasons for using the adjusted r squared. You know, it's not something I'm going to teach in this class, so. Any case, the value of r squared is about 0.7674. I'll throw in the 5 there for good measure. That's not too bad. So it means the line is explaining about 76%, 77% of the ups and downs in the variable y. But did anyone click the plot here for that? Now the cool thing about StatDisk is that automatically it gives you the plot of the data. And here's what happens. Your software package, the least squares line fits, you know, here someplace, and that's not too bad. But is there a facet of the data that looks, I mean, does this look like a line kind of data? Not exactly. So it looks like you can do better. Now I'm not sure how to do this with StatDisk, but I can show you with Desmos. Here's that same data set, and when I fit a line here, I get a value of r squared that matches what we got just a minute ago. But what if I fit something a little bit more? What if I put in a squared term into that? Now how well does your line fit?
Perfectly.
Yeah, it looks pretty perfect to me. In fact, it looks exactly perfect. And you can see that it's perfect by looking at the value of r squared here. R squared in this case equals 1. It's explaining 100% of the ups and downs just by knowing the value of x. Knowing the value of x tells you exactly what the value of y is. So now you have everything in between for your values of r squared. R squared can be anything between 0 and 1. So 0 is less than or equal to r squared, is less than or equal to 1. 1 means you're describing 100% of the variability of your data. 0 means your data is just random. And then you could have everything and anything in between. Now, what value of r squared would you be happy with? Kind of depends on your circumstances. In a lot of the hard sciences, like physics and chemistry and stuff like that, you expect really good results. You expect a high value of r squared. But if you're in the social sciences, maybe a sociologist trying to explain human behavior, good luck on that. There's a lot of things that we just can't explain, all right? That there's too much variability in people's opinions and actions that defy explanation. So your value of r squared might be 0.3 or 0.2. I'm not sure exactly what value they'd be happy with, but it's much harder to get higher values of r squared in some situations versus the other one. But the value of r squared is a measure of how good your model is doing. You want values closer to 1 than they are to 0. So let's run another experiment there. Let's take a look at, we'll do example E and then we'll run our experiment. But before I move on from the coefficient of determination, any uncertainty about that? Something about the coefficient of determination that you don't quite understand? Given one, you can get the other one. Going from here to here, you square things. From here to here, you take the square root. The only thing you have to be careful about with the second one is that sometimes you want the negative square root, not the positive square root. It's going to depend on the slope of the line. If the slope of the line is down, you want the negative root. If the slope of the line is up, you want the positive root. Other than that, you should be good. Okay, let's move on to example E. So it says use the given equation to find the regression equation, examine the scatter plot and identify the characteristic of the data that is ignored, etc. Well, right now what I want to try and do is I want to try and figure out which of these plots actually represents the data here. So that's this part right down here. Now you could graph this and dump in the numbers into StatDisk pretty easily, especially considering that I've got a link for you giving you the data. But if you're stuck with having to do this by hand, one thing you might notice is this right here. You've got the same two values of x here at 13, here at 13, with different values for y. One of them is 9.24 and the other one is 12.99. So it's about 13 and 13. So those two different values should be on the same vertical line. So you start looking around. Well, you look for x equal 13, you look for two values to be about the same, and that would be with this graph right here. Now there's nothing wrong with just dumping this into StatDisk and plotting it. Just want to point out that there's a different way to do this one. Just by realizing that, oh, those are the 2 points that they're talking about right there. Okay, let's move on to example F. And this time I do want you to copy over the data. So again, that's in that Desmos link, or not in the Desmos link, but in the Google Docs link. So if you go to your Google Docs, then you should see example F. Copy all that data and paste it into StatDisk. Now you can clear out all the old data if you want. I'm just going to paste it into columns 5 and 6. You can use any two columns you want. Just remember where you've got the data. So it says, using the pairs of data, find the regression equation of the line. So we'll do that. Analysis. Correlation and regression. I want column 5 for my x's, column 6 for my y's. Yours might be a little bit different. So, okay. How does a regression equation do? What statistic here, and there's a lot of them, what statistic do you think I should look at in order to figure out, how good of a job my regression equation is doing?
Correlation coefficient R.
Correlation coefficient, and what's related to that one as well? Coefficient of determination. So the coefficient of determination is about 50%. You should also look at the plot. try and make sense out of the plot. And there's our plot. Does it look like our line is a pretty good fit there? Yeah, not bad. But you can kind of tell that a lot of what this somewhat good fit seems to be relating to comes from the influence of this one point. That one point seems to kind of make or break your data. So let's do an experiment. Let's take that point out of your data. And what I want you to do is I want you to do two things. First of all, delete that, which is the last point in your data set. Just delete it right off the face of StatDisk. Rerun your regression, look at your R squared, and look at the plot. See what happens when you do both of those things. Try and make sense out of this. Think back to some of the stuff we did earlier. So I'll give you a minute to do that. Kind of walk around and see what you have to say about the results.
What's the value of R squared?
0.
Back to the plot. What's the slope of that one? What's the slope of that line?
0.
Let's take a look at the plot. What's the slope of that Let's see your plot.
You can move that value, so go back to your data. That's just get rid of that last pair.
And then rerun the regression.
Did you notice that R squared? Did you notice the value of R squared? 0.
Okay. So when we do the analysis, correlation and regression, columns 5 and column 6, we get a dramatic difference in the results here. Rats. There we go. Now all of a sudden we get an R squared of 0. And when we look at the plot, we can kind of understand why. What's the slope of this line?
0.
It's 0. Because knowing the value of X tells you nothing about the value of Y. I mean, Y could be above, could be low, could be right on. You just don't know. So if you had to do a hypothesis test here, do you think you'd reject or fail to reject H naught such that B1 equals 0? Yeah, fail to reject. Your p-value is 1 here. That's about as big as a p-value can be. In fact, it is as big as a p-value can be. So you would absolutely fail to reject. The regression model that you would use is just y equals, or y hat equals the average value of the y's, which in this case is 4. So not a big surprise there once you get rid of that one little outlying data. That makes it what's called an influential point. And there's a link here if you want to read more about influential points. But that one is, as I said, very influential because it turns R squared of 0 into an R squared of about 50%. And it also means you have significant regression. So definitely a very influential point. Hopefully we'll get back to doing a problem like example G here, maybe after the break. But for now, there's one last link that I want you to follow off of this homepage, and that's to this one. It's a link called CodeApp, and that should open up something that looks like this. This is going to be kind of a fun one. It's also going to be a little bit interactive. So you should open this link up, and then once you get here, let's look at a particular data set. This is going to go back to that Cedar Point example that we talked about earlier. When you click open, let's see, there we go, roller coasters. You should find the roller coaster data set. So open up that roller coaster data set. So, once again, you're going to click the drop-down menu here, and then scroll down to click roller coasters, and then click open. So everyone who's trying to follow got that open. James, got that open? Almost? No? Did you find the link off of D2L?
Yeah.
Okay. So underneath this menu, that little triple of lines, click open, and then click roller coasters from there. All right, good deal. So everyone's got that data. This is a really cool data set because it talks a lot about the roller coasters that we have in the United States, where they're at, what park, name of the coaster, the max height, the max speed, the type, the year that it opened, etc. So a lot of really cool stuff here. And let's see. There's one that was pretty interesting that we looked at a YouTube video of earlier. Where is it? Right there. Top fuel dragster. And if you click on that one, it actually highlights that data point in this data set. So I'm going to make this a little bit smaller, and I'm going to get rid of this. You've actually got 2 copies of this data set. We'll use them both. I'm going to make each of them a little bit bigger, so you can just kind of follow along. If you're an aficionado of roller coasters, what's the cool or fun thing about being on a roller coaster? What do you like the best about a roller coaster? Speed. Yeah, pretty easy. You want to go fast, you want to be scared, so it's speed. So let's see how we can do explaining speed. So what I want you to do is I want you to take and scroll around, let's see, top speed. Click and drag on this. And it's important not to double click, just click and hold it, and then drag that over to the y-axis of one of your data sets. And then let go. And you should see some wonderful self-assembly. Turns into this nice little kind of sideways histogram. And way up at the top, you can see top fuel dragster, which is kind of way out there, which is nice. But the big thing is, well, what would you use to explain how fast this goes? Which of these variables? Was it the year that it opened? Was it how long it is in terms of the length? Was it how long it is in terms of the time? Is it the age group it's in? What is it that explains the speed? So for instance, maybe we think it's the type of roller coaster. So I can click and drag this down to the x-axis. And all of a sudden you'll see it separate a little bit. And that doesn't really look like it's telling me much about what goes fast and what doesn't. So let's look at something else. Maybe the length of it. And you can click that and drag it down to the x-axis. And that looks like a little bit better. Does it look like there's much of a linear relationship here? Not really. So click the ruler here. And when you click the ruler, you can click least squares line. And it throws on a couple numbers here that are pretty helpful. One is your linear regression, And the other one's your value of r squared. Does our value of r squared suggest that we're doing a pretty good job here? Looks like about 0.296. I think it's best summed up as meh. That's not so good. So what I want you to do, and you've got a couple different data sets you can do side by side, is look at a few of these other variables here. Max height, drop, length, duration. I guess we didn't do duration, but drag those onto the x-axis and see if you can't find something that looks better. This actually looks worse. Duration in seconds. Look at its value of r squared, 0.027. That's horrible. So try and find something else, either between the max height or the drop, that better explains the top speed. So I'll give you a minute to fuss around with that. What should you be using to evaluate which regression is best? Yeah, the value of r squared. You want to choose the model that gives you the highest value of r squared possible. So let's drag max height down here. That looks a lot better. You can also drag drop down here. And then I've got to put top speed up here. Remember, you're going to have to click that ruler and add in the least squares line on the right-hand side. So just click on the graph, click the ruler, add in least squares line, and try and decide for yourself which model is better. Maddie, which one are you liking? Do you think the max height or the drop provides a better predicted value of the top speed?
Probably the max height.
Okay. Matthew, do you agree with that?
I feel like it could be the drop because the points are a lot closer to the line.
Okay, so we got a split decision here. Someone want to settle this?
Drop because the r squared is bigger.
Yeah, r squared and the drop is a little bit bigger. Talking about 84% versus 79%. Not a huge difference, but it is a little bit better in terms of predicting the top speed. And as far as what I would expect on an exam, I guess I would expect you guys to go for the higher value of r squared. Now, there might be some reasons for choosing one model versus the other one that go beyond this, but if you're just taking kind of a nice simplistic approach, it's the highest value of r squared here is what you're going to choose. So, nice. All right, comments or thoughts on our roller coaster example? That data is actually in one of your data sets. If you wanted to play around with it yourself, load it into StatDisk, you could kind of replicate some of those things. But I think that the max drop is the best value of r squared that you're going to get out of this. Any other comments or thoughts here? Okay. Actually, I think we have time to finish up example G, so let's do that. Let S be the sales of frozen food bowls in millions in the years. That is T years since 2000. A reasonable model for frozen food sales is this. S equals 32 T plus 312. What's the slope?
32.
32. Good. So slope is 32. M equals 32. Well, what does that mean in this situation? Yeah, it's an increase. So we use the bottom one, the slope is 32. The sales of frozen bowls are increasing by 32. And keep in mind the units are millions per year. The S-intercept, which is really our y-intercept in this case, is what?
312.
312. So 312 there. There were 312 million bowls sold in the year 2000. What if you wanted to predict about how many frozen food bowls were sold in the year 2005? What do you suppose I would do then?
Look, 5 in.
Yeah, plug in 5. So it would be 32 times 5 plus 312. So it'd be 160 plus 312 is 472 million. Wow, not so bad. Let me just go back for a moment to one of our earlier problems, and that was the IQ of the husband and the wife, which was this example. Now, the slope of the line in this case turned out to be 1.02, which makes sense. What it's saying is that, you know, the male and the female in a couple like that have about the same IQ, so that's fine. Now, this 0.02 doesn't necessarily mean that men are 2% smarter than women. Not at all. You got to keep in mind that what you're doing when you're finding these least square regression lines is you're minimizing that squared distance. That stuff that we did, where was it? Yeah, back here. You're minimizing that squared distance. So this is just a cold-hearted numerical calculation. It's not designed to make sense or be pleasing in any way. It's just saying, all right, what makes this sum of squares the smallest? And a good case in point about that is this line right here regarding the data that we had for a runner and how long it takes this runner to do certain distances. Here's the least squares regression line. So it's 6.76 times x minus 3.06. There's a problem with this line. It just doesn't really make sense. And it breaks down near zero. What's wrong when we get to very, very short distances with this line? It's telling you that it takes a negative amount of time to run these races. That just doesn't make sense. All right, but like I said, this line is designed to minimize the sum of the squared errors. If I wanted a line that made sense, then I'd probably pick something like this and play around with that, a line that went through the origin, because then a race of 0 miles takes you 0 minutes. The problem with that is that eventually this line falls off. You can't hold that same pace forever. You start slowing down with the longer distances, and you see it these longer races. So the best fit comes from this line here. When you get outside of your data, trying to extend this line one way or the other, that's where you could run into problems. So you're just not guaranteed that you can make accurate predictions beyond your data. All right, that's it for section 10.2.